Have you ever really thought about what happens after you swallow a pill? It doesn't just magically teleport to where it's needed. Nope. It actually goes on this incredible and kind of hidden journey through your body. So today, we're going to pull back the curtain and follow that journey, breaking down the science of what we call pharmacokinetics. I mean, it seems so simple, doesn't it? But that one little pill kicks off a whole cascade of events inside you. For that medicine to do its job, it has to navigate your body's really sophisticated internal systems, which are designed to do four key things to it: absorb it, distribute it, change it, and then finally get rid of it. And there's a name for all this. It's pharmacokinetics, which is really just the study of what our body does to a drug. You can think of it as a story told in four chapters: absorption, distribution, metabolism, and excretion. And we have a handy acronym for that: ADME. This framework is absolutely essential for understanding how our medicines work. So let's jump into the first step. All right, Chapter 1, absorption. Before a drug can do a single thing, it has to get into our system. And that means it has to get past a fundamental barrier: our cell membranes. It's got to get past the bouncer at the door, basically. So how does a drug actually cross that barrier? Well, there are two main ways. The most common is called passive diffusion. Think of it like just floating down a lazy river, moving from where there's a lot of it to where there's less. No energy needed. But some drugs, they need a special ferry service. That's active transport. It actually uses up energy and relies on special carrier proteins to shuttle the drug across, sometimes even against the current. The drug's journey always begins at its point of entry. Now, things like injections or skin patches, they offer a pretty direct route into the body. But by far the most common way is just swallowing a pill, the oral route. This is also the most complicated path because that drug has to survive your stomach acid and then make it through the wall of your gut just to get the journey started. Okay, so once the drug is absorbed, it enters Chapter 2, distribution. It's now officially in the bloodstream, which is basically a superhighway ready to carry it all over your body. But here's a really crucial point. Not all of the drug you take actually makes it onto that superhighway. The percentage that does reach your circulation is called its bioavailability. And for oral drugs, this amount is often cut down by something called the first pass effect. As the drug gets absorbed from your gut, its first stop is the liver, which can basically chew up and inactivate a big chunk of it before it ever gets a chance to go anywhere else. Now, for the drug that does make it through, the distribution isn't random. It gets delivered first to the organs with the best blood flow. We're talking the brain, the liver, the kidneys. Only later does it get out to places like your muscles and fat. And what's really interesting is that some of the drug gets temporarily sidelined by grabbing onto proteins in your blood. This creates this inactive little stockpile that releases the drug slowly over time. And now we've reached the climax of our story: metabolism. This is the part where the drug gets fundamentally changed, and it happens mostly in the body's main processing plant, the liver. The liver is, without a doubt, the star of drug metabolism. Just think of it as a super sophisticated metabolic clearinghouse. Its main job is to take these foreign chemicals, which are often fat-soluble, and transform them into water-soluble versions that your body can easily flush out. So where does the real magic happen? Well, deep inside the liver cells, we find these incredible little enzymes called cytochrome P450s, or just CYPs for short. You can picture them as the tiny workers on an assembly line. They grab the drug molecules and start chemically modifying them, getting them ready for the next stage. This whole transformation usually happens in two main phases. In phase 1, the CYP enzymes perform reactions that are kind of like adding a chemical handle onto the drug molecule. Then, in phase 2, other enzymes come along and attach a big, water-soluble molecule to that very same handle. This makes the new compound much more water-friendly and basically ready to be flushed away. But the metabolism story has some major plot twists. You see, some substances can cause what's called enzyme induction, which means they speed up those CYP factory workers. This clears the drug out of your system faster, which can sometimes make it less effective. And on the flip side, other things can cause enzyme inhibition, which slows the workers way down. This can lead to a really dangerous buildup of the drug in your body. And this is not just some obscure science concept. The classic example is grapefruit juice. It actually has compounds in it that inhibit a really key enzyme, CYP3A4.
So if you're taking certain medications, like some statins for cholesterol, drinking grapefruit juice can dangerously spike the drug levels in your blood, which seriously raises the risk of side effects. This is exactly why you see those warning labels on your prescriptions. So, after being completely transformed, our drug molecule is finally ready for the last chapter of its physical journey, excretion. It's time for it to leave the body.
The kidneys are the #1 exit route. They act like this incredibly sophisticated filter, pulling those water-soluble drug remnants we just made out of the blood and sending them out in the urine. Some of those metabolites also leave via the liver, which dumps them into bile. That bile then gets released into your gut, and the drug metabolites are carried out in your feces. So we've followed the drug's entire trip from absorption to excretion. But why does understanding this whole ADME blueprint matter so much in the real world of medicine? Well, the entire goal is to keep a drug's concentration inside what's called the therapeutic window. It has to be high enough to actually work, that's above the minimum effective concentration, but it has to stay low enough to avoid being harmful or toxic. By understanding a drug's unique ADME profile, doctors can figure out the right dose and the right schedule to keep that drug level right in that sweet spot. This quote really just gets to the absolute heart of it. Our bodies have these incredibly powerful systems that have evolved to clear out any foreign chemical. The system doesn't know the difference between a life-saving medicine and a poison. It just sees a foreign substance and gets to work clearing it out. And this really brings us to a final, pretty powerful question. We've seen how our own genetics, our diet, and even other drugs we're taking can dramatically change this entire journey. So, given that each of our bodies has its own unique way of handling things, it really makes you wonder, doesn't it? Isn't the future of medicine all about tailoring the drug and the dose specifically